Hello friends, welcome to another session of EC Made Easy. We are into digital communication world and we are trying to simplify our communication system by increasing the throughput. In this regard, we found that delta modulation can be very much useful. So here, this pink one is our analog signal and the yellow curve is the approximated version of it, and that's given by the delta modulation. So here it says +1 +1 -1 -1 +1 -1 +1 +1 +1 -1 -1 -1 and so on. So if the quantization period, that's a sampling period, and the quantization level are properly matched with the signal, that is the input signal, whatever the quality of the signal we have, and for that property of the signal, if our quantization level and sampling rates are properly selected, then we may get a situation like this, and it would be a better solution. But what would happen if the input signal doesn't always match with? Sometime it changes very fast and sometime it won't change at all. So whenever the input signal is changing very fast compared to the step size and compared to the sampling periods, then we can see here that it is not approximating the input signal correctly. So there is an error here. And this error, whatever we get in this period, is the slope overload error. So this slope is not able to make up with the actual speed with which the input is changing. So it has got a maximum slope possible. So and the requirement is more than what slope our delta modulation system can have. So that's the slope depends on the duration delta t for each sample and delta v, the change in the magnitude for each sample. And the more is the delta t, and the more slowly it changes, and the less is the delta v, the more slowly it changes. So the change, this slope of this depends on both delta t as well as delta v. The higher delta t or lower delta t, lower delta v, or both together, he is going to reduce the slope. So this whole thing depends on the delta t depends on sampling period, delta v depends on the quantization system we have used. So these are going to decide the slope of this staircase produced, and if this is not sufficient enough to follow it, there will be slope overload error. So in order to reduce this, other option is increase the slope. So with the increase in slope, either you can reduce delta t or increase delta v. So increasing delta v means you have less number of quantization levels. So that means the accuracy of representation goes down, and decreasing delta t means you need more number of samples. So either you forego the quality of the approximation by increasing delta v, or increase number of samples by decreasing delta t to follow this. So these are the two ways to take up this. On the other side, when the input is not changing at all, then you see that by mistake, if the quantization level is not matching with the input, then in this case it says that the quantization level is here, so it feels that the input is less, so it reduces. Now for this, input is above, therefore increases, then decreases, then increases, because the actual voltage lies between these two quantization levels, so it keeps moving up and down, up and down, up and down. Unnecessarily your system is transmitting, though nothing was required to transmit. So because there was no change in the input, you could make sure that nothing could be transmitted, but still we are saying go up one, down, go down one step, go up one step, go down one step. So unnecessarily on the other end, you are making the receiving end to compute +1, -1, +1, -1, whereas you could have just said don't change anything. But this is unnecessarily making the secondary to do extra work, though it was not required. So this is what we call the granular noise. So these are the two problems we have with delta modulation. One, the slope overload error, and the other one is the granular noise. And we need some way to find a solution, how to reduce slope overload without increasing number of samples, and at the same time, how can we reduce the granular noise with the available system. So that's what we need to look at. So we wish to look at these solutions in the next videos. So keep waiting. Thank you.